We are given a positive integer n, and we should return the number of binary strings of length n. But this time, as you can see, we are given a constraint, and that is that the binary strings that we take into account should not have any two consecutive ones. So, can you still come up with a formula? Well, it's not so easy with this constraint. Let us see how we can solve this question using dynamic programming. We will analyze the evolution of solutions, and for that, we will start with the most primitive ones, which are the binary strings of length 1. There are two of them, 0 and 1, and both are valid. Now, let us take a look at the binary strings of length 2. They consist of two characters, which we will note by S0 and S1. The difference between these strings and the previous ones is that they have at the end one extra character, which could be either 0 or 1, while the other character, S0, is part of the previous set. What we can do is pick each string from the previous set and either push the character 0 to its end or character 1. But there is one bad string here, and that is 1, 1. Let us see why this happened. If S1 equals 0, then S0 could be either 0 or 1. But if S1 equals 1, we have to be very careful about S0 because it cannot be 1. So in this scenario, S0 equals 0 and only one string is valid, which is 0, 1. And here are the valid strings of length 2. As you can see, there are a total of 3. Let's take a look at the ones of length 3. They consist of 3 characters, which we will note by S0, S1, and S2. The difference between them and the previous ones is that they have one extra character at the end, which can be either 0 or 1. And because the prefix of length 2, S0, S1, also has to be a valid string, it will be part of the previous set. So we can pick each string from the previous set and either push 0 or 1 to its end. But look, there is again another bad string in the second set. Why did this happen? If S2 equals 0, that's fine, there is no constraint on S1. So S0, S1 could be any string from the previous set. But in the second scenario, where S2 equals 1, this doesn't hold true. The problem is when we pick from the previous set a string which has the last character 1. In this scenario, S1 would be 1, and as you can see, we have 2 consecutive ones. So the string is not valid. And this is exactly what happened when we picked the string 0, 1. In conclusion, in this scenario, S1 could not be equal to 1, so its value is going to be 0. This means that the valid strings of length 3 are either of the first type, which means that the last character is a 0, and the prefix of length 2 is part of the previous set, or of the second type, where the last 2 characters are 0 and 1 respectively, and the first character is part of the first set. So they are formed by picking each string from the second set and push the character 0 to its end, then pick each string from the first set and push the characters 0, 1 to its end. And here are the 5 valid strings of length 3. Let's do one more step in evolution and take a look at the strings of length 4. They consist of 4 characters, which we will note by S0, S1, S2, and S3. And of course, they are made of a string of length 3 and one extra character at the end, which could be either 0 or 1. Again, if we pick each string from the previous set and insert the character 0 to its end, and then pick each string from the previous set and insert the character 1 to its end, you will notice that 2 strings from the second set are bad. And you already know why this happens. Because in the first scenario, everything is fine, there is no constraint on S2. So the first 3 characters will form a string that is part of the previous set. But in the second scenario, S2 cannot be equal to 1, so its value is 0, and the prefix of length 2, S0, S1, is part of the set of valid strings of length 2. So what we should do instead is pick each string from the length 3 set and insert a 0 to the end of it, and then pick each string from the length 2 set and insert the characters 0, 1 to its end. And here we have the valid strings of length 4. As you can see, they are a total of 8. At this point, we have figured out a relation between the set of valid strings of some length and the sets of valid strings of strictly smaller length. So let's use this relation in order to compute what the problem asks for, which is the number of binary strings of length n without consecutive ones. This n is very important because it is the only factor that influences the answer of the problem. For different values of n, we will have different answers to the problem. Let's define this answer according to n. dp of n is the number of binary strings of length exactly n without consecutive ones. Back in the evolution of solutions, we can say that dp of 1 is the size of the first set, which is 2. Now, let's remember how the valid strings of length 2 are created. They either end in 0, while the first character is part of the first set. So as expected, there are exactly dp of 1 strings of this type. Or they end in 1, and the first character has to be a 0. So there is only one valid string of this type. But this one also has an interesting significance. Can you tell what it is? 1 is the number of valid strings of length 0. I know, it can be counterintuitive at first to think about how many valid strings of length 0 are there. But this is a trick that you will often see when solving dynamic programming problems, and that is agreeing to the existence of empty states. In our problem, we can suppose that the empty string could exist, so dp of 0 equals 1. Back in the current set, on the second scenario where s1 equals 1 and s0 equals 0, we have a total of dp of 0 valid strings of this type. So, the valid strings of length 2 are created by picking each valid string of length 1 and pushing 0 to its end, or picking the empty string and pushing the characters 0, 1 to its end. You might have already noticed why I have done this trick with the empty string, because now we can see the relation between dp of 2 and the previous two ones. dp of 2 equals dp of 0 plus dp of 1. One more step. For the strings of length 3, we also have two scenarios. The one in which s2 equals 0 and s0, s1 is part of the length 2 set, and the second scenario in which s1, s2 equals 0, 1 and s0 is part of the first set. In other words, we will pick each string from the length 2 set and push the character 0 to its end. Then pick each string from the length 1 set and push the characters 0, 1 to its end. As expected, the first set is going to have a size equal to dp of 2, and the second set is going to have a size equal to dp of 1. So it looks like we also have a relation between dp of 3 and the previous two. dp of 3 equals dp of 1 plus dp of 2. And the same for length 4. We have to pick each string from the length 3 set and push 0 to its end, and then pick each string from the length 2 set and push the characters 0, 1 to its end. The first set has a size equal to dp of 3, and the second set has a size equal to dp of 2. So the number of valid strings of length 4, or dp of 4, is going to be equal to dp of 2 plus dp of 3. So at this point, I think it is pretty clear how each dp is going to be computed according to the previous ones. Remember, you can imagine these dp's as the nodes of some graph. In theory, we call them states. The edges of this graph represent how each dp depends on others. An edge starting from some node and ending in another node means that the value of the second one depends on the value of the first one. In this problem, the value of each state is equal to the sum of the values of the previous two states. This is called the recurrence relation and tells us how we should compute the value of some state using the already computed values of other states. We should be careful because dp of k depends on dp of k minus 1 and dp of k minus 2, but these values should also represent valid states. In other words, k minus 1 and k minus 2 should be greater than or equal to 0. So this recurrence relation can be used only for k's that are greater than or equal to 2. The other ones, which are dp of 0 and dp of 1, are going to be our initial states. And the answer of the problem, which is dp of n, is going to be our final state. Let's see how the algorithm looks like. First of all, we should perform the initialization, which means setting the values of the initial states. So dp of 0 equals 1 and dp of 1 equals 2. Then, the next step is the computation. So for each I between 2 and n, we should compute the value of this state, which is dp of I equals dp of I minus 1 plus dp of I minus 2. And in the end, we should return the answer of the problem, which is dp of n. Because we compute exactly n values and each of them is computed in constant time, the final time complexity is big O of n. And because we just use an extra array, dp, the memory complexity is big O of n. And as some of you might have noticed, yes, this problem is an application of the Fibonacci sequence.